Hi everyone, my name is Ryan, and today I'll be presenting a work entitled ScanpathNet, a recurrent mixture density network for Scanpath prediction. Here is an outline of today's talk. I'll be starting off with an introduction to the Scanpath prediction problem. I'll be presenting related work in the literature. I'll be discussing the theoretical model of our work, which is the guided search 6.0. I'll be proposing the model entitled ScanpathNet. I'll be presenting the experimental results, and finally a conclusion. Visual attention enables humans to rapidly analyze the environment. In fact, it acts as an information processing bottleneck to ensure that the human's limited visual processing capabilities are allocated to the most important region in the image. As a result, it allows humans to focus on important objects. Take, for example, in this scene, we can say that there are specific regions of interest that can catch your attention almost instantly. In fact, it can be represented as a saliency map or a probability distribution of fixations, and can be overlaid on the same image as this. So the white portions of the image tells you how likely attention can be allocated to it. However, in reality, the way that humans attend to regions in the scene is that it is done sequentially. For example, here we can see that if attention can be allocated firstly on the right-hand side, and you can say, oh, this person is looking somewhere in the scene, and you can follow that, and then there's a person looking down, and then you allocate your attention based on what you're looking at. Now, over the years, these problems have been tried to solve by different researchers. So there are two main problems here. First is the saliency map prediction, and the other one is the Scanpath prediction. On the left-hand side is the saliency map model. They typically focus on purely spatial distribution of fixations. As a result, they lose temporal information. On the other hand, Scanpath models tries to model the sequence of fixation, and as a result, the fixations are dependent of each other. Now, saliency map prediction problem can be considered a mature field with several models being introduced yearly. For example, there are EDNs. There are also models that use deep learning, such as DeepGaze, Salicon, DeepFix, etc. There are also models that use generative adversarial network architecture, such as SalGAN. On the other hand, there are relatively fewer Scanpath models, but for the past few years, there have been an increase in the number of models being introduced. The very first model is the model introduced by ET. What it does is it takes a probability distribution, a static one, and it chooses the region with the highest probability, chooses that, removes that region, and then chooses the next highest probability until you exhaust all the possible regions of interest and generate the Scanpath. There are also models that use information maximization theory. There are models that simulate brain computation. Some use gravitational laws. Some also use deep learning models such as RFC, SalTNet, PathGAN, etc. Now in this work, we want to focus on Scanpath prediction during free viewing task and on images. Now, the models that I have introduced or briefly discussed before, most of them try to use statistics, physics, biology, and deep learning to be able to model the temporal sequence of fixation. In this work, we want to be inspired by the latest new, model in neuroscience, which is called the Guided Search Strategy 6.0. So, however, it is important to note that this model is used for visual search, so we're just going to remove the left-hand side where visual search happens, but it is important to note as well that our model can be extended to visual search tasks. So how does this theory work? First, information from the world is encoded into the visual system. It is believed that our brain computes different features and processes them in the visual system. Now, due to the limited processing capabilities of our brain, we can only attend to several objects in the scene, probably 2 or 3, but we can still see information around those objects, which is the periphery. So a part of that feature information is being transferred into the visual awareness field, and then as I mentioned, attention is allocated to very few objects. However, how is attention allocated? It is believed that there is a priority map that is being computed in the brain, and the peaks of those priority maps are the regions where attention is allocated. But how do we actually generate those probability distribution or priority maps? This theory proposes that there are different guidance, such as feature guidance, top-down and bottom-up approaches, or what papers usually use in the literature, as well as there are 3 new types of guidances: this scene guidance, the value guidance, and history, and all of these guidances contribute to the computation of the priority map. Now our ScanpathNet follows or is inspired by the guided search strategy. As a result, we have a visual system, so information from the world is encoded using convolutional neural networks, and a part of the information is encoded into the visual awareness. And then there's also a selection bottleneck that happens, and the history is encoded using convolutional LSTMs. And the scene information and the historical information are combined using a mixture density networks to generate a probability distribution. And the peaks of that probability distribution is where attention is allocated. Here on the right is just the unfolded sample of the model. Here we have the visual system, and here we encode the previous fixation history, multiply them together, and pass it on to a conv LSTM, and then followed by an MDN to generate the probability distribution that evolves through time. As a result, given an image, ScanpathNet can be able to generate probability distribution through times, and then choose the fixation location at the peak of that probability distribution, and repeat that several times to be able to generate a sequence, such as that. Now for the comparison, we evaluated it with different datasets, as well as compared it with different traditional and deep learning models. The datasets that we use are OSIE, MIT, and CAT datasets, and for the evaluation metrics, we use ScanMatch, Multimatch, and Qualitative Comparison. Here is a quantitative comparison, a table that you can refer to in the paper for more detail. In summary, our model has close performance to the state-of-the-art on datasets, and it also beats state-of-the-arts in several datasets. Here is a qualitative comparison wherein on the top here is a sample Scanpath model labeled temporally, starting from fixation 1 to fixation 9, for example. And the figures on the bottom are the sample outputs of different models. Here you can see that our model closely resembles that of humans and performs better than the other models. Here is another sample output of the models in comparison with humans. And as you can see, our model closely resembles that of humans and performs better than the other models. In conclusion, ScanpathNet is a deep learning model inspired by guided state, and despite its simplicity, it has shown promising performance in both qualitative and quantitative results. Thank you for listening. If you have any questions, I'm happy to answer them. Thank you.